Hi guys, this is Mrs. Gastler, and in this video we're going to be talking about the relationship between frequency and wavelength. So we're going to be talking about what those things are, and also how we can do some math with that to solve some problems. So let's go ahead and get started. Whoops, let's not do that. Okay, so when we distinguish between them, so let's talk about what they are. So frequency, first off, is it's how often a wave happens or how often a wave passes a particular point. So we use the letter F to represent frequency. It's a lowercase f, and sometimes it looks a little curvy when we write it. And when we write out the definition, it says it's the number of waves that pass in a given amount of time. And usually that given amount of time is 1 second. And when we measure it, it's a number, but it's a number per second, and that is called a hertz, which is abbreviated HZ. And it's spelled like the car company where you can rent cars, Hertz Rental Cars. Have you heard of that? It's seen the commercials. Hertz, HZ was a guy. He studied waves. Hertz is what it's named after. So HZ, Hertz. So when we say 50 hertz or 60 hertz, we mean 50 waves per second. Okay. Wavelength is, this one's a really hard definition. It's the length of a wave. Yeah. You're probably going to forget that. Make sure you write that down. Length of a wave is wavelength. Okay. It has a really funny symbol, and this one you might have to think about how to write. It looks like this. That is the Greek letter lambda. Okay. It's a lowercase lambda. The capital lambda looks like the letter L. Lowercase lambda looks like this, and it's kind of like writing an X, but you lopped off one of the bars at the top. Okay. And so that's what it looks like. That's the symbol for wavelength. Okay, now when we measure it from crest to crest or trough to trough. Actually, you can measure it from any point as long as it's an identical point. And you have to be really careful with that. So if I were to draw really fast a quick example of what not to do. So it wouldn't be from here to here. That would be no. That is not a wavelength. Okay. But I could measure, let me draw it with a different color, from here to here. That would be okay, because that would be a wavelength, because I'm measuring from a spot that is the same as the next one, okay? When we measure the wavelength, it's a length, so it's just like any other length, and we measure it in meters. And the way those guys are related to each other is like this. So when we put them on a graph, which you have seen in an activity probably, or will see in an activity, is that when you increase the frequency of a wave that is going at the same speed, the wavelength goes down. So the more you write it, and there's a picture down here we'll draw. So it looks like this. It looks like this inverse curve that we've seen before in some of the things that we've looked at. And so they have this inverse relationship. So as frequency increases, wavelength decreases. So that's our relationship right there. This is only true, though, for a constant wave speed. So if you change the wave speed, that may not necessarily be true. When we do calculations, there's some formulas that go with that. And so it looks like this, because it's an inverse relationship. Wave speed equals the frequency times the wavelength. And sometimes you might need to find the frequency, which is the wave speed divided by the wavelength, and sometimes you might need a wavelength, which is the frequency divided by the wave speed divided by the frequency. There we go. Now these are the pictures that I was talking about, and this is what you've probably seen in a lab or will see in a lab. High frequency waves have a short wavelength, so when they're moving really fast, they have a lot of little wiggles, so they look like that. So that's a high frequency and a short wavelength. And then if they have a low frequency, there aren't very many waves passing, they probably have a long wavelength like this. So they have a low, there's not very many that are passing, and so they have a long wavelength, okay? So we're going to practice doing some math here. And in our first example, we have a sound wave that has a length of 7 centimeters, which is 0.07 meters. That's the actual number we're going to use. And we have a frequency of 4,900 hertz. What is the speed of this wave in meters per second? So the equation that we have to write down is this one. And that equation is one whole point all by itself, okay? Without numbers in it, okay? And then we have to plug our numbers in it. So we're going to take the frequency and we're going to multiply it by the wavelength. So that's going to look like this. So our frequency, oh my gosh, did I miss a number? This should be a 9 right there. Look at me. You know, you make some mistakes, right? Okay, so 4, 9. And then I have awful handwriting when I write it this way. 4900 hertz. I wonder if I did the math right for the answer. We'll have to check it. Okay. I got my calculator ready. All right, so I've got my numbers here. As long as I plugged the math in correctly the second time, then I would get a whole point for my work here. And then there's my answer. Let's see, 49 on 494,900 times 0.07. Nope, I definitely have the wrong answer also. Whoops, okay, well I did just erase it there. Let me fix my answer here. This is the wrong answer, and it is 343 meters per second. I should have known that that was the wrong answer because I know what the speed of sound is, and it's 343 meters per second, not 200. That should have tipped me off. That's okay. But now that I have the right answer, that would be worth 1 point. Actually, the number part is half, and the answer part, or the unit part, is half of a point. Okay. So my original work that I did here would have only gotten me 2 points because I did have the right unit and I did try to put some numbers in there, even though I put the wrong number in there. So I would have gotten some credit. Okay. So let's look at our next example. Hopefully I did this one better. Okay. Sound waves travel slower in cold air. What would be the frequency of a sound wave with a wavelength of 0.75 meters? If the speed of sound is 331 meters per second. Now, it says sound travels slower in cold air, so maybe you're thinking, hey, look, that number is not the same as it was in the last problem. 331 is less than 343 because it does go slower through those cold particles, okay? So this time I'm looking for the frequency, so F equals V over lambda. So I've got to put the wave speed on top and the wavelength on bottom, so that's going to look like this, 331 divided by 0.75, and I end up with 441.3 hertz. Now, if you're wondering how in the world did I end up with hertz for the unit, that's underneath this red bar. If you don't care about that, you don't have to write this part down, and you can just accept that it's hertz for the unit, and then you can skip ahead a little bit here. This is what's happening, and I'll kind of highlight as I go along here, as long as my highlighter isn't too huge. There we go. Is that big? Yeah, okay. So right here, what I have to do is I've got meters per second, and I'm dividing it by 1 over seconds. Wow, that's not even the right one. Okay. You know what? Let's just cover that back up, huh? Okay. So what happens is, let's try this again. Okay. So my meters cancel out, and I'm left with my per second, which is what a hertz means. That's where my hertz comes from. That's why the answer for my frequency is hertz. I wonder if I did that on the next one too. Man, I'm just not doing so hot on my math here today. Does this ever happen to you? Maybe you know how I feel. Okay, last one. Maybe I can do this one right. A radio wave that is emitted by your cell phone has a frequency of a whole lot of hertz. What is that? Million, billion, 2 billion hertz. Okay, the speed of these radio waves is the same as the speed of light, which is 300 million meters per second. What is the wavelength of this wave? Okay, so I'm going to be using... That is not the right work for this problem. Who did this? We'll fix it later. Okay, here's what we're going to do. We're going to go like this. Delete. Okay. Ready? Okay, so now we've got to find the wavelength. 2 billion, whoops, hang on, I got to write down my equation first because you have to write your equation down. Wavelength is the wave speed divided by the frequency. You're going to have to be patient with me and my awful handwriting. Let me shift this. It's going to make weird noises. Okay, so I need 2 billion. I can write better than this. There we go. Okay. Nope, I'm looking for... There we go. Wavelength, which is wave speed divided by frequency. Okay. 2 billion. Million. Billion. That's not the wave speed. That goes on the bottom. That's the eraser tool. There we go. On the bottom. Okay. The speed goes on the top. 300 million meters per second. Meters. Nope, that one's hertz. Hertz. There you go. Okay. See, I'm not perfect either, okay? Now I have to plug that into my calculator. That's a lot of zeros though, and I don't want to type all those in. So did you know that when you have numbers like that, 300 million, I'm going to do it down here so that we don't get confused up there. That's not a point. And 3 billion, that you can, for all these zeros, you can just cross them off. I think I'm short some zeros. No, I'm not. So I'm really doing 3 divided by 20 in my calculator. 3 divided by 20. And I get 0.15. .15 meters. Wow, that's a wave that's big enough I could see it, if I could see it. Because 0.15 meters is 15 centimeters, and that's something that I can measure with a ruler, okay? So that is the wavelength of this wave, okay? So that's the answer to this question for real, okay? I'm sorry about all the mistakes there, but those are how you would work through the problems. Maybe the mistakes can help you understand that it's okay to make mistakes, and then you just keep going and you fix them. If you have any questions about how that works, or you need to see some more examples in your packet, just ask your teacher for some help. Thanks for watching.